Are we good? All right. Welcome, everybody. Happy holidays. Merry Christmas. Season's greetings. My name is Paul Ehrlich. I'm the president of the Minnesota Woodworkers Guild. We're a membership-led organization, all volunteers. We have about 850 members. We do a couple of big events a year. One of the events that we do is something called the Northern Woods Exposition. It's every April at the Eden Prairie Center. We usually have 50 to 70 pieces, spectacular quality work. It's open for anybody to enter, but it is a judged event. So if your pieces come in, most pieces are typically judged. There's fantastic cash awards for the winners and bragging rights. And that event is every April. Registration for Northern Woods should go live next month. And as Ed would tell you, if you're not working on your project now, you should be. The other big event we do every year is something called the Expo. And we do that, we've done that the last 2 years at a spectacular location in the Progress Building. It's many of you know it as the Eco Experience Building at the Minnesota State Fairgrounds. It's a great event. Last October, we had about 2,000 attendees. 2,000 plus attendees and about 100 exhibitors, all kinds of craft and everything from a tool swap outside to members' work being shown inside to vendors showing and selling products and materials and some educational stuff that goes on. The third big piece that we've traditionally done every year is an educational piece, and we've done this as a rebuilding year, and we backed up on what we're doing for education, and we're in the process of building a new education program. And that's going to start rolling out next year. We're going to start doing classes that are both online and in person, and there'll be a lot of details coming out about that. It should be a very, very exciting program. We do programs every month. We have special interest groups that meet typically once a month, and one of our special interest groups happens to be a CNC special interest group, and Donovan is actually in charge of that group, and several of us are members of that group. But we have groups in box building. There's a very, very active design special interest group that meets every month at Rockler, plus several other groups. Another great reason to be involved in the Guild is the work that George Lucas, and George is one of our board members, our vice president here, does with our supporters and sponsors. We have 30 plus, 40, 50 plus of our supporters, everybody from the obvious suspects like Rockler and Woodcraft to specialty sawmills, places like Hirschfield, and our latest supporter, our newest supporter and sponsor is Sherwin-Williams. So everybody from people that are doing finish to hardwoods to plywood, even some online retailers that are all part, and all of them give discounts to our members, and we really appreciate them. We actually have one of our supporters in the room today, and Hans is actually the CEO and founder of TSO Industries. TSO does things like things that will go on various track saws and accessories and hold downs and specialty pieces for specialty work. Hans is actually looking for some new talent in his organization, and if you're interested in a career in that sort of thing, you should see Hans at the end of the meeting.
What I'm really hoping to do is to just get the word out in the field through you for people who are technically trained engineers, and particularly people who are problem solvers by nature. You know, for example, people that grew up and worked on the farm. You know, they don't order for Amazon. They go out there that afternoon and fix it themselves with whatever they have. That kind of problem-solving mentality really works well from the kind of innovation stuff that we do for a living.
Great.
I'll leave some cards up
Great.
front. If you take some along, on our website has a career spot on it also. We're going to get a notice up there about these openings. So this is an outreach program because we trust your word of mouth more than some online.
And we'll be posting this on my hopefully the first monthly newsletter this month. If not, it will continue to be an email newsletter that I put out every month. So.
I'll leave these up.
Thank you, Hans.
TSO is trying to hire a bunch of people.
Yeah,
Very much so.
yeah.
At all levels.
Yep.
At all levels. We're
Great.
growing.
Great. There's also some DVDs in the back. If you're interested, these are free to take. and help yourself. And I think there's actually some cookies and pizza left in the back too, which are once again up for grabs, along with water. So, and glue, and the glue samples as well from Franklin. One of the things we do at the beginning of every meeting, anybody here who is new to the organization, it's your first meeting, if you'd like to stand up and introduce yourself. Anybody? We're all experienced? That's great. I think that's a first. Ed, have you ever seen that before? No, I haven't either.
They're all staying away.
Yeah. So before I introduce our speaker for tonight, we're going to do some door prizes. And Dan, if you want to give me a hand. All right. All right. So this is for a broad shoulder apron. I actually have that apron. It's a good apron. Last three numbers are 971. 971. Stu, congratulations. Next. Oh, we got a lot of stuff tonight. Bench cookies. 4 bench cookies, not just one. 966. All right, congratulations. All right, what's the next prize?
More bench cookies.
More bench cookies.
But you're missing. Those are bench cookies plus.
Oh, really?
Yeah.
Wow.
It says right there on the label. Come on, Vanna.
The previous ones were bench cookies minus. 987. 987. They're Christmas bench cookies. Let's do something else. Jeez. What is this thing?
A PSA sanding block.
PSA
Does not
sanding
stand
block.
for public service announcement. It stands for pressure sensitive adhesive. Big old
PSA sanding block. 978. 978. Excellent. You can figure out what it is.
Do a report on it at our next meeting.
Yeah, yeah. Oh, here, something always valuable. Push stick. 981. 981. All right. Your chance to keep the rest of your fingers, Donovan.
Everyone's.
Yeah, everyone's a winner. Our
More
next
bench
prize.
cookies.
More bench cookies. All right.
Bench cookies plus.
979.
I think that's me.
That's you?
I will put them back.
No, it's okay. Good.
I got.
You got. All right. Would you want the clamps?
Yeah, I'll trade it in for.
You can trade. You can trade. I'd allow you to do that.
All right.
All right. All right.
Now.
Now for bench cookies. 982. All right. And for the last set of bench cookies, 964. 964.
Seems like a loaded.
All right. All right. So our program tonight is on a topic that I find very interesting, which is what we call CNC, or computerized numerical control. CNC is the concept of trying to use a little bit of automation in what we traditionally think of as a very traditional craft. And it's a challenging thing to do because you've got to know a little bit about a lot of things, none of which are incredibly intuitively obvious. So, you can pick up a chisel and try and figure out how to use it. CNC, you've got your design, which is all done on the computer. You've got your code, which then drives the machine, and then you've got your machine, which is going to do whatever it wants. I can tell you a lot of things not to do with CNC. I can tell you fewer things about what to do right. But Ed, who was our former president for 8 years of the Guild, is a very, very adept CNC user and has been a member of our CNC SIG in the past and is going to be our speaker for tonight. So Ed, thank you very much. I will swap with
Thank
you.
you,
Oh, you,
Paul.
are you
I've
already?
got one.
You already got one.
Just gotta go live here.
All right.
I'm B. I'm hot. Okay. Well, hi, everybody. Thanks for coming tonight. I'm glad that our regular Tuesday night meeting wasn't this month. It would have been really hard getting here last night. It was bad enough tonight. So like Paul gave a nice introduction, and
I'm going to touch on the things he said and hopefully a lot more. So this is just an introduction to CNC woodworking, very specifically. I'm going to be kind of walking around back and forth here today because I got lots of things to show you and no remote control for the computer. So anyway, I'm just going to give you an introduction to the CNC router, okay? CNC routers are only one of the tools that a woodworker might want to use. It's the only one that I have, so that's one I'm going to talk about. So, like Paul said, it stands for computer numerically controlled. The technology had its infancy in the 40s and 50s, in the machine tool industry, where people were trying to, automate their machines. They used to have to do it with geared trains and all kinds of mechanisms and devices, and they started getting into using electronic actuators and stuff that they actuated with the old punch paper tape stuff that they used to use for teletype machines. And as technology of the computer world progressed, it's come around to what I'm going to show you here tonight. So there's two types of CNC machining. One is additive, and that's when you add material, and don't take it away. That's your 3D printer. And a lot of woodworkers are using 3D printers these days. The most notable example that I know of, how many of you know Mr. Tony Kubalak? Tony is a phenomenal creator of period furniture replicas. And they're true replicas. He makes them down, to the millimeter, exactly alike. Lots and lots of carving. Well, in the past, the only way to do that was to go to a museum and take lots of photographs and stick rulers next to them, and so you had something to go by, and then look at them when you got home in your shop and try to create things. Well, what Tony's doing now, he's taking a 3D infrared scanner, takes that to a museum. He's able to do a 3D scan of the entire piece of furniture without touching it, which all the curators at the museums just love. Tony comes home, he converts that into a digital file, puts it into his 3D printer, and he makes a 3D printed copy of that piece of the furniture that he's going to make, and then that's what he carves from. So it's a great tool for folks like that. And of course, opposite of additive is subtractive. Okay, that's when you're removing material. Common hobby tool is using a laser engraver. And Nicholas has got one that he got for a phenomenal price of nothing. And he brought in an example tonight, and I'll pass this around. Laser engravers certainly have their place. It's good for marking. It's very difficult to actually do machining with a hobby level laser system. You just can't penetrate very deep. I know a lot of them will cut as much as 1/8 an inch, and people will use that. They'll cut 1/8 inch plywood and make interlocking joints and all that kind of stuff. But I'll pass that around. That's something that you could do with a laser. But what we're talking about tonight is CNC routers, and I put /engraver because what I'm going to show you tonight is actually more of an engraving machine than a router, but it's the same thing, and that's going to be the focus of tonight's presentation. Well, okay, so one of my friends heard I was going to do this tonight, and he says, well, why does anybody want to use a CNC machine? I mean, well, one thing it can do is it can give you an extra set of hands in your shop. Some projects just require cutting things out. And of course, you could set up your machine and turn it on and go do something else. I'm going to show you a couple little projects here later that if you expanded them in size and complexity, using the CNC as an extra set of hands would be very remarkable. And also you can make multiple copies of things. I know at Expo, if you went up to the new member table and became a new member, you get this really nice push stick that Donovan made, and he cut a whole bunch of them out of plywood sheets. And a CNC machine can do that. And again, you can do it unattended, and you can go do something else. Well, so why specifically would you want to use a CNC router in the hobby shop? Well, engraving is the first thing that's on this list here. I've, over the years, made quite a number of these little Doug Stowe designed business card boxes. And this one's got a nice little design on it. I'll pass it around, you can see it. I had a client that wanted to buy a number of these, but he wanted the cover to have a corporate logo on it. So I said, okay, yeah, and I'll make these for you for 25 bucks. Okay, so how am I going to put a corporate logo on this? Well, I've got a wood burner pen. That wouldn't be too cool because it wouldn't look very nice. I said, well, I'll go to the local trophy shop because I know they do engraving, and I'll have them engrave that because it's not a complex design. So I took it to the local trophy shop. This is, by the way, is the design. I'll pass both of these around together. And I said, well, so what do you charge me to engrave that? It took him 4 days to get back to me. And he said, it'd be 20 bucks a piece. Oh, come on, I'm going to make a box for 25. And, so I said, there's got to be a better solution. So I went looking for a solution. And that's where I ended up with this little engraver that you can see here on the end of the table, which I will demonstrate in detail at the end of the presentation. We even got a camera set up tonight so we can put it up on the screen and you can all see what's going on. The other thing that I learned, well, and after I learned the capabilities of that tiny little machine and the kinds of things it could do, I started thinking out of the box a little. Well, I have a small box, but I was thinking outside of it. And I decided that, well, look at that. I can engrave a maker's medallion that I can inlay in my furniture. And the really nice thing about this, it's got my company name and my name, is I can also readily change the year that's on this little thing, and then I can inlay that into the furniture. Now, I could have made this the exact size of one of my Forstner bits, so all you got to do is punch the Forstner bit and plug this in. But I have a whole lot of trouble controlling a Forstner bit on a hand drill, which is what you have to do on a lot of furniture because pieces are too big to get them in a drill press. So I used my CNC machine and I cut out a circle of exactly that diameter in a piece of 1/2-inch MDF, and then I just use what they call a dado clean-out router bit. Put that anywhere on my piece of furniture I want, zip out that hole, and plug in my little medallion. So those are a couple of ideas you can do with engraving. Oh, another project, I didn't have a photograph of it, but a lady contacted me once. She wanted a funerary box for her husband's ashes. And on the top, she wanted an engraving of an airplane that her husband had worked on. So anyway, I used that little machine over there, and I actually engraved, I found the artwork on the internet. You can find a lot of stuff on the internet. Didn't have to create anything, just had to convert it to files that the machine could understand. And I engraved in an aluminum plate and then inlaid that into the top. And it worked really nice. I just should have taken some photographs of it so I could talk about it. The next thing on the list is making signs. So when I first started thinking about, well, CNC is pretty neat technology, maybe I should look into it. Well, I wonder what you could do with it. So I went on YouTube, and the only thing you can do with it apparently is make signs, because that's all you can find on the internet. Signs of all kinds of shapes. But that does come in handy sometimes. This is one that I cut. I don't know if I don't think I can pass it around if you want me to. But I made this on my bigger machine that I have at home, and I'll show you some photographs of it. The client in this case came from, he's part of the Muckler family down in Iowa, and this is now mine because the farm was actually established in 1855, not 85. But anyway, he brought me this old barn board and had me make a sign for him. And I finished it and photographed it and sent it to it and says, it's ready for pickup. And he says, what happened? It's supposed to be 55. Oh, he says, tell you what, I'll get another board and bring it to you. So that's what we did. But this is the one that we ended up with. And I'm going to talk about this board a little bit later because of its physical size. So that's making signs. Oh, here's another sign. I should do that too. I made this sign a few years, well, a couple of years ago. It's on a piece of melamine. It was CNC routed with a technique called V-carve. V-carve is a technique that you use, well, you use a V-shaped bit, and when you set up the programming for the machine, the V-shaped bit, when you get into these really fine detail areas, it actually comes and rises up, so it only uses the tips, the tip of the piece. So I routed all this out, and then I filled it in with colored epoxy, so it's an epoxy inlay, and then just sanded it off. And because it's melamine, it was pretty nice to surface. So it was just a fun project we do for the 4th of July. Another thing you can do with a CNC machine is make inlays. Sunday afternoon, I decided I better have an example, so I made this. Okay, so that's walnut lettering inlaid into this piece of Baltic birch. So you just set up your program, you do 2 tool paths. We'll talk about tool paths later. One tool path, you cut around the outsides of the letters to make the letters. And then the other tool path, you carve inside the letters to make the recesses. And then you just put them in there and glue them. You don't have to fuss around. There's no sanding or fitting, or it just slides right in. And I didn't have anything more fancy to show you than that tonight. You can also cut precision router templates. I already talked about the little template I made to put my medallion in. A couple years ago, I had a project. I was building a table, and I had to join some 3-inch square hard maple. It was a trestle table, basically, is what it was. And I wanted to put double. I use loose tenons all the time. I want to put double tenons in the uprights. And I was thinking, okay, so double tenons, and I can make a jig, or how am I going to control the router and make sure the spacing is exactly the same on both parts? So I got out my machine. I used my bigger machine, not this one, and I made a couple of templates using the same computer file. One that would fit on the bottom of the uprights and give me perfect registration, and the other one that would fit perfectly on the cross member and give me perfect registration. And then I used a piloted router bit and cut my mortises, and everything just lined up really great. So you can do stuff like that. And then the thing I found it to be most useful for, whoops, what happened to my, it should say, there we go, make specialty parts. This is a project I made for a client about this time last year. The client is an aficionado of old International Harvester tractors, and he has reproductions of them and the like, but he wanted a clock. So this is a clock. It's about 2 feet tall and about 1 foot wide. It's all wood except the headlights. The headlights are real. They don't function. He wished they did, but they don't. And what I found the CNC machine really good for was making these two, the numerals and the logo. As you can see, they're in 3D relief, and I was able to program them. And they're cut out of hard maple, so I get really good fine grain. And then I set it up so, okay, the router cuts the outside, and then it goes in and it cuts the relief on the inside, and then they're just painted. That's something I could have done without the CNC machine, but it would have been pretty hard. I could have scroll sawed the numbers out, and then scroll sawed out a little some really thin stuff here and glued it on, and all that fussing and bothering. But it turned out to be really easy to do that way. There's another one. This was an interesting project. This is just a 3D image taken out of Fusion 360. This is the foot that goes on the base of a table that I made for a client. And the way I made this thing, I took a log of maple. It was about 2 inches square. Ran it through the table saw, cut out that corner, and then made a piece to fill that corner, and glued it in with brown paper in the glue joint. So now I had basically a 2x2 log that I could put in the lathe. I turned the pieces, turned them round, turned in the grooves on the sides, cut them to length, and then just chiseled that piece out that was held in with the brown paper. But before I did that, I decided, well, I got to cut the grooves in here. So I checked the bugger up on my lathe. I don't consider myself a turner. I make turned parts for furniture. I chucked that hard maple foot up on my lathe, and now I'm going to cut these grooves here in end grain. Well, you can imagine where my chisel went. It went everywhere. I tried 3 or 4 of them, and I said, no, that's not going to work. I'm just not skilled enough to do that. Gee, I wonder if I could route that in there. So that's what I did. I just made a clamp to clamp it down on my bigger CNC machine, programmed in those 2 grooves. This one is an 1/8 inch wide, and this one's a 1/4 inch wide, and you can easily get 1/8 and 1/4 inch bullnose bits. Put those in there, machined that out in, I don't know, 30 or 40 seconds, flipped it over, did the other side. It solved a whole big problem. I didn't know how else I was going to do that. What else we got here? Boy, I've got an awful lot of that slide showing up. So I'll take you through the process of using a CNC router. Paul already alluded to it. There's lots of steps. That for hobbyists, woodworkers, that's the biggest drawback. It's once you understand it, it's simple, but getting started, it's not simple. It's not like putting a mark on the end of a board, taking it over to your table saw, flipping the table saw on, going through the complication of getting out a miter gauge and putting that on, cutting the board and turning the saw off. Using a CNC router's there's a process that you have to go through, and that's what this is about. The very first thing is you have to have a digital design of this thing that you're want to make. Now, you can do digital designs in so 2-dimensional is just doing something like a Christmas ornament, okay? You put the tool in, you run it around, your part's done. 2.5 dimensions is like those numerals in that IH logo I showed you. It's the router running and creating stuff on different planes, but they're still planes. And then on 3D, that's when you're actually cutting contours and curves, and I'll show you some examples of that. And it's another level of programming that you got to get into to do that. Oh, now back to the 2D. You don't have to use a digital design program to create a digital file for a CNC machine. Excuse me. You could use a flatbed scanner. You could take a drawing, you could even do a sketch. Say if you wanted to do something free-form, you sketch it out, put it on your scanner, get a digital version of it, PDF, whatever, and then you can put that information into the digital program that creates the G code. Okay, so that's the first step. The first step is you have to have a digital design. It's got to be in a digital design file. Then you have to take that digital design, that file, and either feed it into a separate computer-aided manufacturing program, or most of the digital programs designed for CNC have this feature embedded in them. So you only need one program. But it's the second step that you have to do. Once you get the design done, now you have to design how this part is going to be manufactured. Very first thing you have to do, you have to define the coordinate system. Okay, and right there, that scares a lot of people away, okay? Because they remember when they were in junior high school and they had to make plots on XY paper, how confusing it was. Well, you got to get over that because you've got to work with coordinate systems. Most machines are 3 axis, X, Y, and Z. So and you have to become familiar with that. So you have to define the coordinate system. That is, you have to develop instructions that tell the machine where is 0 in this design. Because everything is referenced from that 0 point when you're cutting. And I'll show you an example of some G code. You can kind of see that. Then you have to figure out, well, what kind of cutting tools, that is, what kind of router bits am I going to use to make this? For instance, if you're going to make that sign that's going around, you have to use a bit that's a V bit. Okay? If you're just going to cut out a shape like this, you could use a cylindrical bit. If you want to do a lot of 3D work, you're going to have to use a tapered ball nose bit. Because if you try to do a 3D carving with a straight bit, the only thing you get is a bunch of steps. So you have to know what kind of tool you're going to have to use, and you have to tell that to the program. You also have to figure out how fast you're going to spin that tool and how fast you're going to move that tool. Now, most programs have all that stuff built into them. You can pick the tool, and it will give you suggestions on what speeds and what feeds to use. And as you gain experience, you can change that stuff to however you think you want to do it. Okay, so once you get that stuff decided, then you have to convert that into a set of instructions that the machine could understand, and that's called G code. I don't know what G code stands for. It's G code. And then that program then has to take that G code and process it one more time to put it in a format and a style that your specific machine can understand. They're all a little different. And then the next step is to connect your computer to your CNC machine and then use another set of software that will send that code to the machine. Now again, if you spend a lot of money on a piece of software, it's going to do all 3 of these things. I'll be showing you the cheap, easy way to get into this. It's with free software, and you're going to have to use more than one kind to actually finish this job. All right, and then the process. Okay, now you got your computer. It's plugged into the machine. Now what am I going to do? Well, you have to affix your workpiece to the machine. You can't just throw it on there and have something happen. You have to hold that piece tight somehow with mechanical fasteners. I'm going to show you a really easy way here on this little machine. We're just going to use double stick tape. But you do have to hold it down. And then you have to go through the process of instructing the machine as to where 0 is for your design. A lot of people will default when they're making something, and they'll say, okay, this is 0. Everything that on this plaque will be defined from this point. Sometimes that doesn't make sense. Like the little pieces I'm going to show you I'm making today, 0 is going to be in the middle, because when I want this piece finished, I want a nice even border around here, and I don't want any irregularities in the shape of this piece to mess that up. So I'll define 0 as at the middle. That sign that's going around, I also defined 0 being in the center. And yeah, I'll show you. And the reason for that is that this board is too big to fit into my router, my CNC router at home. My CNC router is 17 by 17, and this is 12 by 24. But I defined this as the center when I created the digital design. And then when I went to tell the computer how to run the tools, and I used tools plural because I defined it 3 times. I defined it once to cut this, just the word muckler, using that as the center. So I put this in my machine so that I could get that word and the center all in that 17 by 17 square. When that was done, I moved the board, and then I said to the machine, okay, center's moved over here now, but go ahead and cut this. And I did the same thing for the third one. So you can, with a little bit of ingenuity, you can put big pieces in your smaller machines without any trouble. All right, and then you got to set up dust collection as required. Tonight, I'll show you, we're not going to make a whole lot of dust, but we still have dust collection. And then you start the job, you press go. And then you might have to make tool changes as you go along. And I'll show you that again tonight, because this little piece I'm going to make requires 2 different tools. Now, the expensive machines have automatic tool changers, and the program will tell it, well, go get this tool and go get that tool, and this one doesn't. Okay, so a little bit about digital design software. As I mentioned, you can generate a 2-dimensional design from a sketch just by scanning it. Or you could create it from scratch in the digital design tool. And I've got one on the computer. I could show it to you tonight if you want to see how that works. All these programs I'm going to show you tonight give you a wide range of different kinds of tools that you can pick from to do your design. And they give you guidance on proper speeds and feeds, which I already mentioned. So, what kind of digital software can you get? So here's simple software, and it's free. Okay, the most common one that people are familiar with is SketchUp. So you can do digital designs in SketchUp for free. The latest way to do that is online, but it's a good tool. And then there's Fusion 360. There's a free version available, although I learned this weekend it's getting to be more difficult to get a hold of. But I've used that a lot the last several years and made some pretty spectacular stuff with it. One that I like for simple things, like making that this inlay. I whipped it out in, like I said, 20 minutes this weekend, is a company called Carbide. No, it's called, I don't know what the company name is, but their software is called Carbide Create. And you can get Carbide Create for free, but you want to make sure you get version 6 or earlier. Because if you get version 7, they went the way a lot of companies are going. Although the software is free, you can no longer create a computer file to send to your CNC router unless you have one made by them. So I use version 6. A couple other ones, FreeCAD, Desk Proto, and then Easel is a pretty common one. You can see a lot of YouTube videos where people are using Easel, which is a free software package. They all operate pretty much the same and all pretty much have the same capabilities. And then you can get into the comprehensive ones. Okay, these are the programs that will do everything all at one time and provide lots of flexibility and better design features. And they're anywhere from $200 to $2,000. Mach 3 is a big one. A lot of commercial CNC folks use that, along with Vectric and Aspire. Carbide 3D has a pro version, as well as VCarve, And then, of course, Fusion 360, if you have the paid version. The paid version doesn't offer any additional features regarding CNC, but it does offer some different design features. And then Carveco Maker is another one. Again, you can find all of this stuff all over the internet. So most of the digital stuff that I showed you, all of these programs over here, come on, except for SketchUp, will actually create the G-code. SketchUp, you have to have a plug-in to do that. So when you're creating a G-code, you have to define the capabilities of your machine. You have to tell them the program, and remember I told you you had to post-process your G-code to fit your machine. You need to tell the program, well, physically how large is my machine? And how fast can I run the spindle? Because then when it goes and creates the G-code, if it senses that you want to cut something that's outside the capabilities of your machine, it'll let you know that, okay? So you don't end up ruining something. And then, so then the program goes through and it creates all the motions that your machine needs to go through that are tailored to the capabilities of your machine. Here is an example of G-code. This is the G-code for the piece I'm going to be making here tonight. And this came out of Fusion 360. This is the way it does it. You can see everything here with an open parent on it. That's just a comment in the code line. So, but it is really handy because it tells you, and by the way, this comes out as a text file. And that's how I'm able to print it here. And it gets sent to your CNC machine as a text file over a serial interface. So here it's showing what the vendor of the machine is, what its model number is, what the description is. This is an XY axis on the table, and then a Z axis on the head. And it says there, you see there T1. That's tool number 1. I could have defined a number of tools, and it would have gone down and told me what each tool was. But because my machines don't have tool change capability, I just have to set them up one tool at a time. Anyway, it tells me tool 1. It has a diameter of 1.418 millimeters, and it has a radius of 0.75 millimeters. Everything on these machines runs metric. You can design in English units, but when you generate the G-code, it generates it in metric. This tool also has a 3.2 degree taper on it, so it's a tapered ball nose bit. And the minimum Z height is in there. And then it starts giving you these codes. G90 says, okay, everything is going to be measured in absolute numbers from 0. And it goes down, and it's got G21 that says this is in metric. And then it goes down, another G90, T1. Okay, here, S means speed, so it's going to spin the spindle at 7,500 RPM. And M3 says turn the motor on. And then G54 says, I'm using the coordinate system called G54. You can actually define different coordinate systems. So, for instance, if you're making multiple parts on the same sheet of goods, you can say this one is a G54, this one's G55, this one's G56. And the machine will now know which set of coordinates to follow. And then it says, okay, first thing, go to X, 18.277, Y minus 17,995. And it just keeps doing that. It just keeps spitting out these commands, and the machine keeps making those moves. And that's how you end up cutting something. Oh, it also says what the feed rate is. And if you listen to this machine when it's running, you'll hear that the spindle speed changes often and the feed rate changes often. That's because I use Fusion 360, and they have this super optimization algorithm that they use for absolute best cuts. And all the other programs I use don't do that. So that G-code then is sent to the machine. And I mentioned earlier, you usually need a separate program to do that unless you buy one of the expensive commercial things. 3 of the most common free programs, which are you can use on both a PC and a Mac. UGS, Universal G-Code Sender, I'll show you that running here tonight. There's another one called Candle, and if you happen to buy this little machine here, it comes with that, which runs, oh, that one only runs on Windows, I'm sorry. And then there's a crowdsourced program called Open Builds Control, and you can get that on both Mac and Windows, and it used to be called Bob's CNC. Bob and his buddy went out of business, and now Open Build just runs that. But all of those will send the G-code to the machine, and they all have different interfaces. You operate them differently, but they all get the same job done. And as I mentioned, some machines require a proprietary G-code sender. Paul, your Onefinity, what does that take?
So the Onefinity and most of the bigger machines have their own built-in controller.
Yeah,
So you take your G-code file and you load it into the controller
yeah,
on the machine.
yeah,
And then it runs it. So the Onefinity has a couple of options. It either has a Buildbotics, which is an Arduino, or the Masso, or now they have a third controller.
uh-huh,
But most of the bigger machines have their own controller that you can actually watch what it's doing instead of feeding it.
yeah. So, and a lot of the other machines have their own controllers too. Okay, so say you've decided, well, I want to try a CNC machine. Well, where do I start? Well, your choices are nearly infinite. That's unfortunate. You can find prices anywhere from the hundreds of dollars up to the thousands of dollars. Most of them are what they call 3-axis machines, X, Y, and Z. That's common. You can some of the hobby machines you can actually buy another device to fit on them that gives you rotary motion. So you have now a 4-axis machine. And they'll run on either 2 principles. One is a moving table, and you'll see tonight on my little machine, the table moves in the Y direction, and the spindle moves in the X and Z direction. But more commonly, when people see a CNC machine, they're looking at something that has a moving gantry. That is, the motor will move X, Y, and Z with the table being stationary. Neither one is better than the other. It turns out for small machines, to make them simple, moving the table is better. Big machines, we're going to put a much larger piece on it. Moving the table is not a good idea because now you got to move the table, wait for it to stop, wait for it, the momentum to dissipate before you can do the next operation. So they just do it with a gantry system. So there's different kinds of mechanisms for machines. In the early stages of hobby CNC machines, almost all of them ran with a cog belt drive, where the servo motor, and I guess I'll talk about servo motors. The servo motor would be connected to a cog belt, and then that cog belt would be fastened to one of the axes of your machine, and then moving a cog belt back and forth would cause the machine to move. Frankly, that's a lot faster than the more common mechanism, which is a screw, but it's also for very light loads. It's very good for engraving, and a lot of laser CNC machines still use cog belts because it's very fast and you're not moving a lot of mass. One of the downsides is it does require frequent maintenance because those belts stretch, and as they stretch, you start losing your indexing. 0.001 is no longer located at 0.001, it's at 0.0015, so now your geometry gets all whacked up. So you just have to maintain them. And the next, the most common that you'll find these days is either lead screws or ball screws. A ball screw is just an expensive, high-precision lead screw. You can get a lot of power through that system, a lot more than through a cog belt. It is generally slower than a belt drive just because of the mechanism that's involved. It requires little or no maintenance because there's nothing to stretch. You're talking about all steel parts running together. The only time you run into a maintenance problem is if you start using your machine so much you start wearing out the metal parts. And that is the most common for small shops. And I already mentioned the ball screws. Servo motors, okay. Servo motors are the little motors that make everything move. Okay, and what's different about a servo motor from an electric motor? Well, servo motors, they used to be called all the time stepper motors. But I haven't seen the phrase stepper motors for quite some time. They're all servo motors. So basically what a stepper motor is you send it a digital pulse and it rotates a specific number of degrees. And it depends on the design of the servo, how many degrees it's going to move. But every time you send it a pulse, it will move exactly that many degrees of rotation. So then your machine and all the software that's involved in here to create the G code knows how far your machine's going to move when it sends one pulse. So it figures out, okay, if I got to move from here to there, I got to send it this many pulses, and it'll do that. So there's two kinds of servo motors, open loop and closed loop. Open loop is definitely the most common. Until maybe 2 years ago, it was about the only thing you could get if you were buying a hobby machine. But now they're starting to have closed loop systems. It's the least expensive, and it doesn't go to without verification. What I mean is that, okay, in my G code, if the G code says go to X4, Y5, it'll go there, and that's it. It won't verify. It won't tell the computer that's running it if it got there or not. Okay, if it ran into something on its way there and it stopped, the computer program thinks it got where it was going, and then it just keeps sending commands. So it's not as goof-proof as a closed loop system. Closed loop are more expensive. You can get better precision with them, and what you get is a go-to with a position feedback. So once it gets to where it was told to go, it tells the computer, I got there, and then the computer proceeds. If it sends a signal to the computer that says, oh, I ain't there yet, then the computer deals with that, either with an error or it slows up and waits for the command to complete, that kind of thing. So this is really a great thing for commercial shops who are running big jobs unattended, and something goes wrong, the machine can sense that and figure things out. Okay, so then how are these things controlled? Well, they're all controlled electronically, of course. Many small shop machines use single board computers, either an Arduino or a Raspberry Pi, little processor. And if you want to come up after the talk is over, you can see the massive controller hanging on the back of this machine here. It's got a one-chip computer and a couple of diodes and a couple of resistors, and that's it. So that controller then receives the computer code, and it comes in through a serial interface. And in some cases, like I'll show you on my bigger machine, you don't have to plug it into a computer. You can run it wirelessly. Okay, so what are the things you need to think about if you're going to get into CNC router work and you're looking to buy a machine? Well, first thing you need to think about is, well, how big a piece do I ever want to work with? So how big a machine do I want? You could buy a 4 by 8 foot bed machine and cut one of these little tiny things on it. That's not a problem. But of course, if I wanted to cut this sign that I showed you on this machine, I'm pretty much out of luck. So you got to decide. It's like buying any other piece of woodworking tool. Well, what am I going to make with this? Or what do I need to make? What kind of tool do I need? So you have to think about, okay, what do I want to make with a CNC machine? So now that can help me figure out what kind of machine to buy. So you need to know what the workpiece size is going to be. Next thing you need to think about is the power of the motor. A lot of machines use or set up all you do is you bolt on a commercial router. Makita and DeWalt, their little routers are very, very popular. And there's a lot of machines made that will directly accept those. It's a very inexpensive, well, you know, what, 120 bucks for a router, I think, these days. Of course, they sound like a router. They're extraordinarily noisy, and they're not terribly high precision as far as the spindle. The spindles, you know, it's made for carpentry, not for precision work. But you can do a lot of really great work with one of these with a router on it. The other option is to go to a dedicated brushless spindle motor. These have much higher precision bearings in them, so you can do much more precision work. They're definitely more expensive. You're not going to get a brushless spindle motor for 120 bucks. It'd be more like 300, depending on what size you wanted. And then one thing they really do offer is that they're extremely quiet. Most of those machines, you cannot hear them running if they're not cutting wood, including this little one that I've got. This has got a little DC spindle motor in it, and it's pretty dang quiet. The other thing you have to think about is tool size. Okay, so once you're thinking about, well, what size pieces am I going to cut? Well, what am I going to cut in them? What kind of tools do I need? Like this little machine here, I can put a 1 millimeter diameter bit in it. You have to be really careful because they sure break easily. But I couldn't possibly cut that sign over there on a machine like this. So you need to know what size bits you're going to use, especially what collet size, 1/8, 1/4, 1/2 inch. Or some machines you buy, you have to think metric. And so you have to think about the tool size capability. A nice feature they have on machines is stops. This little machine here has no stops. If I keep pressing on the button and send it the x-axis, it'll physically run into the end, and then it will start making all kinds of gross noises because the stepper motors are being stripped up, and it's not a good thing to do. So if you have a bigger machine with a lot more power and you want to treat it nice, you put limit switches on the axes. Excuse me.
Want some water?
That would be good. We don't have any here tonight, I see. So anyway, when the machine gets over to that limit switch, it tells the controller, oh, I'm here. Oh, we do have water here tonight. Thank you, sir. So then I'm not going to damage the machine or anything. Also, so you can set the machine up so that when you turn it on, it automatically goes through a routine and figures out where its limits are, and then it says, okay, here's my machine zeros. That's a new coordinate system you have to worry about. Your machine has a set of coordinates, and your workpiece has a different set of coordinates. You want to know if the machine has zero probe capability. So I've been talking about, okay, you make this design, you have to tell the computer where is 0 on my design. How do you tell the machine where that 0 is? Well, the way we'll do it on this machine is you move it around and make sure that the bit is right over your 0 position. You say, okay, that's 0, X and Y. But then this one has a really fancy Z0. I'll show you how that works. You stick that in there, and the machine runs itself, and it finds its 0 in the Z-axis. Nice machines have a little device. It's a little aluminum block with some corner cut in it, and you can usually stick it on the edge of your piece and punch a button, and the machine will go around, and it'll search, and all of a sudden it'll bump into that aluminum piece and say, okay, that's X0, there's Y0, oh, here's Z0, and it does all that for you automatically. It's a matter of what do you want to pay. But you want to have some sort of 0 probe capability, especially Z height, because I'm going to show you here, I'm using two different router bits. I have to change the router bit, and on a machine this size, it's almost impossible to get that router bit in with the exact extension length off the collet, because you got to, depending on what you're doing, you might have to, that might have to be within 0.005 of an inch. So anyway, so you need the ability to tell the machine quickly where is Z for this new, Z0 for this new tool. And then the other thing you get into on larger machines is the ability to change tools automatically. And a lot of them will do that. So here's some commonly available machines, not intended to be exhaustive by any means. Shaper Origin is one that you hear about if you read a lot of woodworking magazines. It's about $2,900. It's a handheld computer-guided router. Okay, so you actually have to hold on to this and run it around, but the computer makes adjustments and for you. It requires full-time operator engagement. When you're making a piece, you got to be there. Except recently, they just released a new accessory that basically clamps this to an XY table, and it will move it around. But it's $2,900 plus another $500 or $600. And to me, being sort of a purist, it just blows away the real purpose of this. Because the real purpose of this is right there. You have an infinite working area. What you have to do, you have to lay. They sell this special tape. It looks like domino pips all over the tape, and you have to put that tape out around your work area, and then the machine has a vision system, and you have to do a little bit of calibration, but then it picks up all these dots. It's moving along, so it knows exactly where it is, and that's how it works. I've seen a lot of custom flooring installers who put really fancy inlaid designs in their flooring will use these, because they can take that to the job site, put it down on the floor they laid, they can cut the inlay they need and plop their parts in. I mean, it just makes a lot of sense. And then a lot of woodworkers use these too. Some I've heard really like them, and some I've heard just sell them after they've bought them. It's got an integral brush type motor, so it's fairly loud, and it requires proprietary software in all realms to use. But then if you want a more commercial thing, an XYZ machine, here is that Next Wave Shark HD 500. I picked this one because it was approximately the same price. You can buy this at both Rockler and Woodcraft. Its working area is 13 by 27 and 7 inches high, which is a pretty good working height. I can't think of what you'd make where you need a 7-inch high working area, but they've got one. It has a pendant here, a touch screen, so you can do basic things like you can move the actuators around and do your zeroing and all that kind of stuff. You still need a computer to send the G code to the machine. You supply your own router. You can see right here, this looks like a Bosch Colt router, probably it is. But you have to supply your own router on top of the $2,700. It does, however, include V-Carve desktop design software, which is a $350 value, but it's only good for 1 year. So after that, you have to buy some more stuff.
Actually, it's good. It's not good for a year. You keep it once you get it.
Oh, do it? Okay, with theirs.
You get the software, and then if you want to upgrade, you get free upgrade for a year.
Okay.
If you want to go to the next version.
Okay.
You know, the upgrade price, but
Okay.
once you have it,
Does anybody here know anything about this Next Wave? I can't imagine why it's $2,700.
actually, I do. I could go along talk a lot about these, but I'm not a fan of them. I think they're overpriced.
Yeah, I would think. I'll show you what I bought for a whole lot less than $2,700.
That's fueled my soul.
Okay. But they're readily available.
They're a great starter machine.
Yeah,
They're available used, apparently.
probably, probably. A real step up from that is something that, well, Paul has a Onefinity, but he's got the, oh yeah, and this is the Elite Woodworker I posted here. That's a $3,300 machine. I had my eye on one of these for a couple of years. I thought, that's what I need to go to. But I could just never digest the $3,300. It's a 32 by 32 working area, which is nice and big. You can do some pretty decent stuff on it. 4.5-inch height. It's got ball screws in it, so it's really high precision, very smooth running, very rigid and stiff, which is something you need in a CNC machine because you got this weight hanging out there. In this case, it's showing a Makita router. You put a Makita or I think a DeWalt in it, but you have to put your own router in it. And it comes with a 1-year subscription of Carveco Maker. After that, you've got to either resubscribe or do what you want. And it has its own controller, so you just feed your G code, and that's what's shown on that tablet there. You feed your G code into that, and the machine works for you. And they're really nice machines. A lot of really nice press on YouTube on them.
And you use your own, you said use your own router.
Yeah.
Just any old router?
No, it has to be the right diameter to fit in the adapter that goes on the machine.
You can use a router, or as you said, you can put a spindle in.
Yeah, you can add some more money to this and buy a spindle and put that on there.
Then you get some decent. The router's a little underpowered for the machine.
Yeah,
So I'm in the process of converting mine to a spindle now.
yeah,
Hoping to do better on profile cuts and other things, because the machine's got a lot of stability, but
yeah,
it's got a lot of wood on the little trim routers.
yes,
Hard.
yes. Yeah, they're not designed for that. And then on a lower price point, Onefinity just came out with this one here. They call it their Apprentice. It's under $1,000. It's a lot smaller. See, 16.5 by 16.5. It's got the same ball screw design as their big machines. It's got some Windows control software that's included with it. And again, you supply your own router for this. So you got all these different price points you can work with. And then you can go the route that I went. This is a Chinese machine. You can either buy it from their website or Amazon. It's the Genmitsu 4040 Pro, $880. 16 by 16 working area with 3 inches of height. It's got lead screws. It's not the fancy ball screws, but it's got lead screws. It comes with a 700-watt spindle motor, and it comes with no software. But that's okay, because all the software that I use, I just download off the internet. It's free. And this is what mine looks like. A little bit of a side view. Well, maybe I could do this. So here it's got a spindle motor on it. This is a 800-watt unit. It's got a cooling fan on the top. This is the dust collection system. This is the hose from my shop vacuum cleaner. Whoops. From my shop vacuum cleaner. This is the controller. This knob I added. When I put the spindle motor on it, it requires a separate power supply. That's back here. And this power supply, the speed control, is no longer available from the computer program. I could work around that, but I decided not to. So this is the speed control for my spindle motor. This little device here, this is a $30 add-on that I went to. This gives me the ability to control this machine wirelessly. And I did that because I didn't like having my laptop in my shop because the keyboard gets all gunked up with sawdust and everything. So I just use my iPad. And this company makes an app for the iPad that allows you to control the machine with the iPad, and you do it wirelessly because iPads don't have any serial interface on them. All these machines require a serial interface, but that little add-on controller here takes care of that. And you can see here, I was cutting that sign on there. And as I mentioned, although that my machine isn't long enough to accommodate the length of that thing, you just got to be a little bit smart and think about geometry and coordinate systems and how am I going to convince this machine that it can do this job? And it goes ahead and it does all of that.
That's a fair amount of dedicated space.
Oh, yeah. Yeah. No question. And none of them are real compact. Of course, if you want a bigger machine, it's going to take more space. Yeah. That's why I didn't want to buy a bigger machine. This one is fine for me. I mean, even this little machine here, look at the dedicated space it's got, because it still has to have a computer someplace to run it. And then here's the last one. This is mine. This is a CNC Top Bayo 1610 Pro. $110 on Amazon, okay? It comes in a box with a lot of screws. You got to put it together. But it comes complete. It's got a controller. It's got the serial interface cord. It comes with some sample files that you can test. It comes with a set of engraving bits. And it also comes with that program I mentioned earlier called Candle, where you can send your code to the machine. And this is where I started. When I decided, well, there's got to be a cheaper way to make 5 of these than spending $20 a pop at the trophy shop. Well, I didn't come out quite. I spent $10 more. Okay, but now I have a new tool that really opened up a lot more opportunities for me in my shop. It's only 7 by 4 inches with an 1 3/4 Z height, very small. It is a lead screw. It's not a belt drive. It's got a little 20-watt spindle on it, which only has an 1/8-inch collet, so you can only run 1/8-inch bits. Well, that's not true. You can run bigger bits that have 1/8-inch shafts, and the software was provided.
Ed?
Yeah.
So thinking about, that's a pretty small table, 7 by 4.
Yeah.
Can you, like, I'm thinking about your farm sign.
Mm-hmm.
Could you have it running much way off the table and keep moving the sign as you?
Yeah, but there you run into a problem of mass on that table because the table moves. And I don't.
Too heavy.
It probably would be too heavy. Yeah, but you know, if you're doing something like on 1/4-inch plywood and wasn't too long, it could probably manage it. Yeah. Yeah. No reason it couldn't. Okay, we talk a little bit about router bits. There's 3 basic types: straight bits, V bits, and bullnose bits. Straight bits you use for bulk material removal and for running outlines and free form working material. Oh, to free parts from the working material. Well, okay, this sign was made exclusively with a 1/4-inch and round flat router bit. And that's why I picked this text, because I could run this text with 1 bit and not have to do any bit changing. So I didn't want to spend that much time on it. And then there's V bits. Use those for engraving. Okay, in order to engrave this little thing here, I just use a little pointy bit. It's a 30-degree V. It's very sharp, and then it only penetrates when you set up your machining code. You tell it how deep you want it to cut. Obviously, if you're cutting with a V bit, the deeper you cut, the wider the lines are going to be. So you just do this a little bit. In this particular case, what I did, I took this maple and I finished it with shellac first, and then I engraved it, and then I took acrylic paint and filled it in, and the acrylic paint wouldn't stick to the shellac. It only stuck to the native wood that got engraved out, so it works out really nice. You can see it easy. So that's what you use that, and for carving the sign over there. And like I mentioned earlier, the advantage of a V bit when you're carving is you can carve a line that's infinitely thin if the bit gets raised up, and when you use your software, they all have something called a V-carve mode, and it will figure out how to cut all the material out of that letter and bring the bit up at the right point to make all the fine detail that you've defined. And then bullnose. If you're making, you know, like a charcuterie board, and you got a recess, you can just use a bowl carving bit that you can buy at Rockler, or you can get one of these fancy tapered ball nose things, which you really need if you're going to do 3D carving. And then another, quote, machine tool that I've included here is the zeroing probe itself. Now in this case, this zeroing probe is really, all it is a little piece of printed circuit board. And what happens is you start a routine on the machine, and it brings the router bit down until it touches. Oh, by the way, you have to take the alligator clip and clip it to the tool so that when it touches, it completes a circuit and says, oh, I'm there. And then to be more accurate, it backs it up a few tenths of a millimeter and runs it back even slower just to verify that that's where 0 is. And then you have to tell the machine, well, how thick is this plate that I just touched on? Go ahead and subtract that from where you are, and then that's 0. So, but you can get some pretty fancy 0 probes. Okay, so now we get down to demo time. Unless anybody's got any questions they want to back up on. Okay, for that, we're going to use our digital HDMI switch right here. And we should be able to get a picture from the camera. There we go. We can see the machine. Now I can't show, come on, wake up. I can't show well, I guess if I turned it like this maybe, you can kind of see. Yeah, that won't work. This program over here, this is universal, pardon me, that's not it because I changed. There we go. This program here on the screen is Universal G-Code Sender. Free program, load it up, comes Windows, got one on my Mac too. And it provides just all kinds of features to operate the machine. It has one mode where you can just press buttons and work the XY axis like this. Where's my mouse? Here we go. It's called the jog controller. I can move in the X direction, X positive. I can go move X negative, and go Y positive. I can move the spindle up and down. And this is what you use to get the thing set up. So before we were started the meeting, I went and I centered, I told the machine where 0 was for this little part that I'm going to make. And this program has the ability, you can write macros. So you just click one button and the machine goes through a bunch of things. So this should go to the center. Okay. That's the bad noises I was telling you about. I forgot to set that up. So we'll do it all over again. I probably better do it the right way here. Okay, I talked about one of the first things you have to do is affix your workpiece. Okay, and this is my workpiece. It's a very, very heavy piece of lumber. I hope my machine can handle it. It's a piece of cherry, and I'm going to affix it with double stick tape. And if you notice, I won't be affixing it to the aluminum table. One of the things, if you're doing engraving especially, or if you're going to cut one of these fancy little designs I've got, the motor must be absolutely perpendicular to the table. Well, this little thing, you know, it's plastic, and the first engraving job I did, I discovered it ain't. So what I did, I put a piece of MDF on here. It's held on again with double stick tape. And I put a little bit bigger router bit in, and I wrote a little routine that just went back and forth, and it milled this board exactly perpendicular to the machine. So that's where everything gets mounted these days. So we're going to put that in there. And I've got this little plexiglass L in here, because when I take this and do multiple demos, I just set it up once and I can just put new parts in there. And then I put the wrong piece in there. This part doesn't have the center marked on it. Good double stick tape. Okay, this piece has got a center marked on it. Okay, so all I'm going to do now is I'm going to run the Z-axis down close, and then I'm going to, whoops, visually find my center here. There we go. And then I've got a macro over here that says set the center. Come on. Okay, so now it knows that this is the center. The big numbers on this screen, on this screen are the, well, it's not X0. There, X0 and Y0, and the smaller numbers are the machine's coordinates. When you turn the machine on, it says, okay, I'm at 0. Well, that doesn't coordinate with the piece of work I've got. So we'll take that off. We'll put our work piece on here. I know X and Y is still 0. Pressing that down really good. Now what I need to do is bring the spindle motor up a little bit. I'm going to take my Z probe here, connect the alligator clip to there so I can get continuity. I'm going to go over here to my quote probe module, and I'm going to probe in Z0. And you can see the spindle's coming down. It touches, goes up a little bit, comes down slowly. Okay, so now it knows where the top of my workpiece is. What I'm going to do is make one of these. Did I send one of these around earlier? These are just some little samples I made. One of the things I've wanted to do for a long time is make a basket weave pattern. So I figured out how to do that. And I'll pass this box around. You can take a look at it. I designed this, I'll call it a program. I designed a thing in Fusion 360, and I used the parametric design capabilities of Fusion 360. And I can go into Fusion 360 and I can change the width of the verticals, the width of the horizontals, their spacing. I can change the size. I can make it cut circles or rectangles. And then I create G-code out of that. And well, here, and I'll send this one around too, because there's a circle one that I told it to make. And then, I don't know, have you all heard about our memory box SIG? We make boxes for the families of, well, for families who have lost a child from medical problems. And this is the lid that I use on my boxes. And you can see I've put the basket weave on there, and it's also got some V carving here, and then it also has some engraving on it. And this all goes on my bigger machine.
Is that lid on this machine or your bigger?
No, my bigger machine, yeah.
You couldn't do it on this?
No, the box that I'm sending around I made on this machine. It's the biggest I can put on there. So anyway, we're going to be making that sample I'm sending around. And to save some time, I'm going to do a rough cut with a 1/8 inch end mill here, or a flat bit. And it's loaded on the machine. I've got, come on. There we go. Got the program loaded up, and you can might be able to see the UGS program will show you the tool path. That's the path that was generated by the CAM program, and it'll show you where we're going to cut. And we're just going to cut a bunch of rectangles to remove bulk material, we'll call it. Although the piece is so small, using the word bulk doesn't seem to be very appropriate. Now you saw the machine go down in a spiral action. That's because of this super sophisticated algorithm that Fusion 360 uses. It's more efficient and gives you better tool life and all that kind of stuff. Can you see really what's going on there, or do we need to change the camera angle? See if we can raise it a little. Come on. Ugh. No, that's about it. You can see it's cutting little rectangular recesses in it. And as it's cutting here, it's showing you the G code that it's processing at the time, if you're interested in watching it, right? In this mode, you can actually see a graphic representation of where the spindle is, what it's completed, and what it still has to cut out. So we'll just let it run. It only runs a couple of minutes.
So is this one program and you asked it to do a rough cut and a final cut, or is it two programs?
It's two programs because I don't have a tool changer. Because I had to tell it instructions for two different tools.
So you programmed the rough cut you wanted,
Yeah, well,
or did you design the rough cut you wanted?
when you set up the design in your design program, it will tell. Well, let's see. How do I describe this? Like I said, some of the stuff gets a little complicated. Fusion 360, for instance, if I say, okay, I want you to cut this design, it will figure out that, oh, I can do a rough cut first, and it will tell you what tool you should select from, and then do it. Otherwise, you have to use your own brain and think, okay, I want to do a rough cut. I'm going to cut this out, but I'm going to do it roughly. I'm going to use a big tool, so the machine knows, well, it can't put a big tool in a small spot, so it won't. And then you do another.
Software will do that, Ed. They'll do that, so they'll
Yeah.
say, you want to design this, and you say, I've got an 1/8 inch bit, a 1/4 inch bit.
Yeah.
It'll dig out the big parts with the 1/4,
Right.
and then come back with the 1/8 afterwards, and clean up what you could afterwards.
Yeah.
A lot of times that's, it's a dual tool path. You
Yep.
do the same thing, but you're
Yep.
two different
Yeah, it depends on the capabilities of the program you have chosen to use as your design tool. All right, so I told you dust collection is always important. It's digital. Okay, so here you can get a pretty good view here of what we've got. We've got a little square with a bunch of rectangles cut in it. Okay, so now what I'm going to do is I'm going to go back to my jog controller. I'm going to raise my bit a little bit. I'm going to bring it over here to the front where I can work on it. because I'm going to change the bit. And my tool changer is not automatic, but it is digital. Okay, and I'm going to put this in there. I know you can't see much of it, but it's got that 2-degree taper on it. It's got a 1.5 millimeter diameter ball at the bottom. And of course, and you use this for 3D carving. It gives you a smooth transition, so you don't get those steps that you get with a straight bit. And because it will actually do some cutting on the sides. And the computer program takes all that into consideration once you define the geometry of the bit that you're using.
Can you open that in front of the small camera? Ed?
Yeah, we could probably do that.
So did your bits cost as much as the machine itself?
No, these bits are really cheap. And they're solid carbide. They're less than $1 a piece. Again, you can go crazy with bits. I buy these from Amazon. They work just great for me. If I was running a production tool shop, I'd probably buy some really high quality bits, pay some decent money for them, and they'd let. But these work just fine. So I'm going to chuck this up. I'm going to tell the machine now where 0 is for this bit, because it's not the same as the last bit I put in. So I got to find, I like going to the middle as much as I can. Because this one's got some recesses cut in it and stuff, I got to be a little careful. But we'll put the
So the XY 0 is the same.
XY 0 is the same. I didn't change it, right?
Yeah, just 0.
Yep. And we'll go back up to the probe module and probe it. Sounds a little crude, doesn't it? Okay, so now it knows where the top of that workpiece is with that bit. Now I got to go load a different program because I got a different tool. And this is medium. This is the finish cut. And you can see here, I don't know if you can see the screen, but these are the tool paths, and you can see there's a bajillion of them. Because we're doing some fine 3D work here, we've got to make very, very small incremental changes in order to make everything nice and smooth. And in addition, you'll notice when the machine's running, it's not going orthogonally. It'll be going diagonally. And that's an option, again, you can get with a lot of programs. Fusion 360 does that. And I discovered in cutting this, it does a whole lot better job on all the end grain that shows in this design. So we'll give this a run. This will take a little longer than that last one. And if you want, at this point, you can kind of come up and watch it or ask questions or see whatever you want, because it'll take about 5 minutes just to run this. As you can see, it's just going back and forth. The bit's going up and down constantly. That's what 3D does. If this was 2.5D, it would just go down to one depth and cut it. And then if it needed to go deeper, it would come back to origin, go down a little deeper and cut it. But this is constantly moving up and down and X and Y.
If you hadn't have done the rough cut and just ran this, would that not turn out?
It ends up being too much material for that little bit to cut out. It would I've never tried it, but it would either get rough or it would just break the bit. It wouldn't take any longer. What's that?
Your cut time would be probably.
Well, the cut time would be just this cut time.
Right.
Yeah, you had to slow the speed. You didn't want to break the bit.
Yeah, you had to slow the speed down, then it would take longer. And Yeah. Yeah, and you can control all of that stuff.
Well, I just want to take a second to talk about the state.
Yeah, by all means.
So we've got a state that's been running for about a year now through the Guild. I'm trying to keep it managed, but Ed was there. We've got a couple other members that are part of it. We meet on a monthly basis, and last year we did, similar to the memory boxes, we did the caskets for the hospital. And we all produced different ones and presented them. We're looking at doing that again this year. We're looking at doing other projects. Now, to be part of the thing, you don't need a CNC. We get people that come in that are looking to get involved in it, that haven't purchased things. We're all there. It's basically just a sharing process of how do you know, if you got questions, we're all just in it together to try to help each other find projects. I'm currently trying to find another project for us, like some toys for maybe a hospital or something like that, some stuff we can do for kids. So we meet monthly. Sometimes we meet in shops, sometimes we meet, we do a Zoom meeting, so we kind of alternate. 1 month we'll do a Zoom meeting, and then the next month we'll do an in-person, either in somebody's shop or typically Devani's, which is close to me. That's because I get to pick. So our next meeting is actually next Tuesday at 7 o'clock at the Devani's. So if people want to come there, they can come there. We do have, Paul is able to set up a Google group now for us. So we can share emails, we can share files back and forth. So we're looking some ways to expand this, and if you're interested, whether you have a machine or not, you know, come in. If you got questions, we've got a number of people with good knowledge that can kind of help with that.
Yep, it's a good group. So that's the end of the presentation. Come on up and ask questions, look at stuff, whatever you want to do.